Okay, section 5. One application of the interference is CD and DVD. Okay, let's see how they work. So data is stored digitally. So we need a series of 1 and 0, right? You know, that's 1, 0, 1, 0. That's instead of 10, we are 1, 0, 1, 0. Okay, so now the data is reading by the laser light reflected from the disk. Okay, look at the disk. Here's CD and DVD. Okay, the DVD you see can store more informations. Okay, compared to CD. So use a different colored light, red light, blue light, for example. Okay, so this part is moving, right? Just like CD rotate, rotate, rotate. Okay, now the laser going to read the signal. Okay, so now let's say CD. Okay, the track consists of series sequence of peaks. So this is like a low part peaks. And then this flayed surface. Okay, when this rotate, this part moving, and laser read this signal. Okay, let's see how it works. So now see this part is moving. This part moving. Okay, see the peaks. This peaks of the peaks. Okay, from here to there. This exactly equals 1/4 of wavelength of the light. Okay, now let's say this part running, rotate this way, and laser beam fixed. At this moment, see this beam, half of the beam reflect from here, and half reflect from the low part. Okay, so now, so the see the difference. So that's 1/4 wavelength, second quarter. So now the distance travels different. Okay, so this half, let's say, 1 reflect this way, and 2 reflect that way. The difference is just equals half of wavelength. So these two are going to cancel each other. Okay, and when the light have this kind of destructive interference, we read as 1. When the light is over here, both from the phase surface, they have same phase, then we have the constructive interference, we read as 0. So when the CD or DVD rotate, laser beam going to read the information, digital information. Okay, that's how the CD and DVD work. DVD use shorter wavelengths of laser, so can store more information. Usually it's about 30 times more than CD. Section 6, we're going to study diffraction. So diffraction is spreading out of light or any wave from initial line of traveling. So the light come out from different openings. Okay, then it's like a wave travel all the direction. Then so many waves going to interference. So we call diffraction. So diffraction has connection with interference. Okay, generally diffraction happens when wave pass through many small openings. Okay, so we're going to discuss some detail. Seems like you have one double slit, another double slit, and many of them work together. That's the diffraction. Okay, here's the device we use for diffraction. We call diffraction grating. Diffraction grating. Usually it's a piece of plastic or glass. But there are many lines. So like many double slit. Okay, look, these ones were like what we're going to use in our lab. So that's 1,000 per millimeter. Think about 1,000 per millimeter. So that's the distance between the two lines is like 1 micrometer. 1 times 10 to the power -6 meter. So that's how they work. Okay, so now we look back this one again. So again, this distance is so small. Remember, the distance between from here to there is 1 micrometer because 1,000 per millimeter, right? So that's 1 micrometer, 1 micrometer. So this distance from the first one to last one is much small compared to this distance from the grating to the screen. That's very important. Very important. Okay, and now we're going to see what happens. So again, we can treat the grating like many double slit work together. And we even assume they all go the same direction like this one. Okay, they all go the same direction. They're parallel to each other because they're so close. So close. Micrometer between compared to the distance from grating to the screens like a meter or 2 meter. Okay, so then we can just go ahead and use the formula for double slit for the grating, the diffraction grating. So this formula is the same. So d sine theta equals m, that's the order, 0, 1, positive, negative 1, positive, negative 2. Then times lambda is the wavelength. Wavelength. Okay, so that's order wavelengths, and d is the spacing. Okay, remember this is much smaller than double slit. That's about a millimeter, and this is like a micrometer. So now let's see what happens. So now for given m and given lambda, if you use same light, so for the grating, the angle will be much bigger because d is much smaller. The angle is much bigger, right? Because if the lambda is fixed. Okay, so that means different color going to separate further away. So we have a better resolution. Smaller d, bigger of the angle, then better resolution. So we can study the different color, different frequency. For example, like the spectrum of the atoms. Okay. So here's to give you a few things about the grating. Remember the formula we're going to use is going to be same, but now the d is different definition. Okay. So now you see this compared to the double slit interference is more sharp. Why? Because for the maximum you have to satisfy all the lines double slit. So that's why it's narrow compared to double slit. Okay, and the different spectrum. Okay, for the prism. Okay, the red goes smaller angle, violet go bigger angle. And for the grating, it's opposite. So violet go smaller angle and red go bigger. Because you see this, if D is fixed for given grating. Okay, longer wavelengths go bigger angle. So red light will go bigger angle, violet, shorter wavelengths go smaller angle. So that's a few things. And we have so many different applications. So when we have a lab, this is one of our lab. So we're going to study how laser pass the grating. So we have different color of laser, red one, a red color and a green color. They will separate different angle. So if you can measure the location of different color, you can determine the wavelength of laser. Okay, then we also can see when the white light pass a grating, then give you like a rainbow, different color separate. It's more like this one. All the color come out. The white light come and different color separate. Now, later, we are going to study in chapter 27, 28, we're going to study atomic physics. So we're going to measure the spectral line, the hydrogen, helium, neon, different atom give you different color frequency, and different color tell you different energy level inside the atom. So that's we can use the diffraction grating to check and determine the different frequency from different atoms. Okay, so this when we have a lab, I'm going to give you a similar demonstration. Now the third wave nature, we're going to study the polarization. We have many applications like sunglasses. So now we study how this polarization happens. So light is one type of EM wave we already studied. So now the EM wave travel this way. That's the electric field, and then magnetic field. They are perpendicular, and both perpendicular to traveling direction. Okay. Now the natural light, like sunlight, is like this. So now we're going to discuss only electric field because usually it's more important. Okay. So now if you see the light, really electric field go all directions. Go this way, travel forward, that way, and this way, go all directions. So this kind of light we call unpolarized light. Sunlight is example. But now the sunlight only go one direction, only go this way, just like that. Only go up and down along one direction. But most lights will be like this, go all directions. Okay, so now sometimes we want to use polarized light. So how we can change from this one to that one? There are three ways to make a polarized light. The first one, we can choose selective absorption. Some special materials absorb the electric field from one direction but not another direction. Second one, we can use reflection. Third one called scattering. Okay, so this time we're going to study only first two, selective absorption and reflection. Okay, so one famous polarization device we call polarizer, polarize. Okay, it's like a piece of this. Some sunglasses, well, you probably pay more, gonna have this function. Okay, if you look through from this polarizer, you see inside is darker compared to outside. Compared to outside. Why? Because half light cut off. The light go, say, this direction, cut off. The light go that direction, left. Okay, look this. So this can pass through. Okay, that one, well, only part can pass through these components. This one cannot pass at all. Okay, that one also only part, this part, can pass through. Okay, so now, so totally you're gonna have half light pass, half light not. Then after this polarizer, you're gonna have a light like this, only goes same direction. Okay, so now the reason the polarizer is like this piece of materials, and okay, we have a long chain molecules as one long molecules, another, of course, many of them. Okay, so now the electrons in the molecules only move horizontally this way. So when the light goes this way, so the electrons going to absorb energy. Okay, the electrons do not go that way. Do not go that way, only horizontally. So if a light comes this direction, this direction, the electrons will not absorb energy. So that's why this is the axis, perpendicular to these long molecules. So now after light, see natural light, unpolarized light, pass this piece material, what happens? The electric field will always go this direction and not that direction. Okay, so now let's see what happens. This unpolarized light pass polarizer, and this one here gives you direction. So now after light pass this polarizer, okay, then what happens? Only this direction can pass. So now overall 50% of light cut off. Only electric field go this direction, the light can pass it. Okay, so now if I have second one, you can rotate the second one when this line and that one parallel to each other. Then you have a same light pass second one. But if this line and that one, they're perpendicular. Okay, if perpendicular, what happens? So this light already go this way, cannot pass second one. Because second one, the axis is perpendicular. Okay, so now if you rotate this one at any angle, well, then some light can pass second one. Okay, and we have this equation. Now I, the first time we study this, so I is the intensity of the light. The definition is intensity is watt per meter square. Intensity of light is power of light per unit of area. Okay, so now this is the I's output, and I sub O is the initial intensity, and the cosine theta square, and this theta is the angle between the two polarizers. Okay, so we are going to have some demonstration, and we're going to measure how light pass first one, pass second one, then we're going to rotate second one, see the change. See the change. How we're going to study this. Now the second way polarization can happen by reflection. Reflection. Okay, again, suppose here's the light go from first medium to second one. Let's say from air into glass or into water. So now we studied in chapter 22, reflection, right? The light is going to reflect from surface. Okay, this angle and that angle always the same. The incidence angle always equals reflection angle. Okay, so now some light going to enter second medium from air into glass. Okay, so now the angle in glass is going to change because light slows down, right? So in glass, the angle will be smaller. In the air, the angle always bigger. But if you go backwards, of course, okay, from the glass into the air, then the angle going to be bigger, going to be increased like that. Okay. So now, okay, we can change the incident angle, right? Okay, when we change this angle, reflection angle going to change, but always keep the same. Then at the same time, this angle, refraction angle also change. Okay, so now suppose the incoming light, incident light is unpolarized. Okay, so then we check this light, reflection light. Okay, we're gonna find when this angle change until this angle, incidence angle plus refraction angle equals 90 degree. When this angle plus that angle equals 90 degrees, then what happens? Then reflection become polarized. Okay, so the light will go only in and out the paper, and not the perpendicular part. See, so this is going to disappear only the okay, this one and that one means the electric field go in and out the paper. Okay, so at that special angle, then the reflection light, okay, become the polarized. So that's polarization by reflection. Very interesting. So in next lab, we're also going to check this. We're going to change different angle until reflection become the polarized. Okay. So now, one application I'll call you sunglass. If you look, you have a boat, you play, say, the lake. So now, the if the sunny day, you know, the reflection light from the water surface always bother you, right? But if you wear sunglasses and at a right angle, then what happens? The light going to be reflection light going to be cut off, right? Because reflection light supposed to go this direction, but your glass only let this direction pass through. So you still can see outside, but no reflection light from water surface. Okay, so now we're going to do a little mathematics. So that angle, special angle, we call Bruce angle. That's called the scientist's name. This special angle we call theta p, Bruce angle. I don't know why don't you see the B, instead you see the P. Okay, so this angle happens when theta 1 plus theta 2 equals 90 degree. Okay, so when theta 1 plus theta 2 equals 90 degree, look here. So when this incidence angle plus refraction angle equals 90 degree, then reflection become polarized. Okay, so now we're going to find it. Okay, we start with this equation. Remember, we call the law of refraction from one medium to another. Suppose from air to glass, from air to water. Okay, now for air, N1 almost equals 1, right? Okay, so now when we assume we have Bruce angle, we want to find the angle equal to what? So if the incident angle equals Bruce angle, then the theta 2, by the definition here, equals 90 minus theta 1. Now, right now, the theta 1 equals Bruce angle. Okay, so we have theta 2 equals 90 minus Bruce angle. Okay, and also assume it's from air. So N1 equals 1. Then N2 we just call N. So this is going to be equals 1. And we swap the 2, just use N. Okay, so now we're plugging all the information here to that law of refraction. See what we got? So N1 equals 1. And theta 1, sine theta 1 equals sine theta p. When theta 1 equals Bruce angle. Then equals N2, which is N now. Sine theta 2 and theta 2 equals what? 90 minus that Bruce angle. So now the law of refraction becomes this: sine theta p at Bruce angle equals n sine 90 minus theta p. And you know the sine 90 minus angle equals what? Cosine of the angle, right? So this becomes n times cosine theta p. Okay. So now if we divide by cosine term both sides, sine divided by cosine give you what? Tangent. So we're going to have what? Okay, sine theta p divided by cosine theta p, which give you tangent theta p. Tangent theta p equals n. Tangent theta p equals n. So the angle equals tangent minus 1n. So if you know n, you can find that Bruce angle, right? Okay, so for example, the glass n equals 1.55 and water n equals 1.33, then you can find which angle will give you the polarized light. Okay, and okay, here I'll give you an example. You can calculate. It's pretty straightforward. Okay, so the first one, when n equals 1.52, okay, part B, n equals 1.33, and you tell me what is Bruce angle. Okay, that means from the glass, at which angle reflection become polarized light. And then from the water, n equals 1.33, at which angle you can have reflection become polarized. Okay, so I want you email me your answer. I'll give you this week to finish. Rest part is not required this semester, but if you have time, you can read it. I'll give you some more discussion. Okay, so thank you.